היי, מה נשמע? יופי. הזדמנות טובה. כן. דומה מאוד, כן. לא היית אז, גדי. כן, עכשיו... שוב פעם? You can't get enough. אין בעיה.
Good afternoon. Pleasure to introduce Rubin, our speaker today. Ron completed his bachelor's degree as well as master's degree in physics at the Hebrew University. And he's currently finishing up his PhD with Chaim Sompolinski
at the Hebrew University.
At the Hebrew University. And next month, is that right? He heads to Columbia University where he'll be a postdoc at the Center for Theoretical Neuroscience.
Hopefully.
Hopefully. Yeah. And he also told me that he hasn't won the Nobel Prize yet. Okay. Today
just because you asked, not.
Just because I asked. Today he'll tell us about his work on learning precisely timed spikes.
Okay. Hi everybody, thanks for coming. So this is work, the main part of my PhD work, and maybe you've heard Chaim talk about it a few months ago. If so, maybe you'll feel better asking me questions you wouldn't have asked Chaim. So feel free to interrupt whenever you want. So this is work I did with Chaim, and these are collaborators throughout the years: Remy Monasson from Paris, Raoul Memmersheimer from Nijmegen in the Netherlands, and Ben Solovetsky from Harvard. So I want to start with presenting in like 5 words the usual approach for neuronal learning, which goes something like that. So when we talk about learning neuronal computation and learning, what we usually have in mind is that we have some network of neurons with some connectivity matrix, and that network receives some input in the form of firing rate, maybe static, maybe a function of time. And the goal of learning is to change the synaptic weights of this network in such a way that the output of the network, so let's say we have 2 neurons that we call them the output neurons, or these are neurons that we care about what they do for some behavioral task. So we need to change the synaptic weight in such a way that the output of the neuron will be some desired output. Okay, and we do it in all kinds of ways. We present the input and see what the output is, change the synaptic weight, in what is called supervised learning. And the goal is to match this desired output. And everything is usually framed in the language of firing rate. How many spikes per second, or what is the temporal profile of the firing rate of the neuron. But what we want to claim is that rate, describing the system with firing rate might not be enough. So first of all, neurons have spikes. They don't have just firing rate. They have spikes, and if we want to, we want to describe them as accurately and capture all the phenomena as accurately as possible, we need to have some framework to do learning and computation with spikes. And second, in many systems, for example, the barrel cortex in rats, the firing rate is very, very low, and the firing is very, very sparse, or the processing that the animal does is very, very fast. So the entire description of a representation with rate becomes a little bit unreasonable, because how can you, in order to talk about rate, you need to average over some long period of time and talk about some mean quantity. And if all the decision is made based on a few spikes, then rate doesn't make sense. And in addition, some experiments found that at least the information about the stimulus exists also in the spike times of neurons that respond to stimulus and not just the rate. So it's a question whether the brain can or does use this information, but at least we know that in some systems this information exists. So our goal, our main goal, is to go from the previous pictures with rates to this kind of picture of neuronal learning. So to develop a framework that will have the same network with the same connection, but now the input will be some given series of spikes of all the input neurons, and the goal of learning will be to change the synaptic weight in a way that will enable the output neuron to output a specific sequence of spikes in particular times. Okay? Questions until here? Yeah.
So what's the biologically plausible accuracy of...
We'll talk about it more.
What's an example of a system that has sparse time coding?
For example, the barrel cortex, the average rates are a few hertz, 1 or 2 hertz, in response to whisker movements. Okay, that's one example. Yes, HVC is also an example. It's an area. We'll talk about the bird song. It's an area in the bird where when the bird sings its repeating motif, each neuron fires only one spike or one burst of spikes at a certain time. Okay. So what we did is start with the simplest case of trying to develop the theory and framework for learning precisely timed spikes in the most simple architecture possible, a singular network where we have an input and one connected directly to one single output, and we want to learn these kind of transformations. So to be more precise about our model, we consider a leaky intricate and fine fire neuron. So this is the scheme. We have some inputs. So the x-axis here is time, and the y-axis are the different input efferents, input neurons to our readout neuron. And this is the activity pattern of that the neuron receives. Each bar is one input spike. And these spikes are summed linearly with some synaptic weights to produce the memory potential, U of t. So here is the memory potential in response to this pattern. So, okay, this is resting potential, and this is the threshold. So the neuron integrates the spike. Each input spikes causes one postsynaptic potential like this in the memory potential. And every time the memory potential reaches the threshold, there is a spike and reset, etc., etc. Okay? So what's important, so here is an expression for the memory potential. What's important to notice is that it has two parts. The one is the subthreshold potential, the contribution from each of the efferents, summed linearly with some weights, omega I. Okay, where xi of t is just this sum on all these postsynaptic potential kernels. Okay, so every time there comes a spike from efferent number 1, we add this function at this time, at the time where it arrived. And the second part is the part that corresponds to the effect of the reset. Every time there's a spike, we model the reset by adding by resetting and continuing integration. The effect is adding another kernel. And what's important to know about this part is that this part is very nonlinear, right? Because this X reset depends on the times of the spikes. So when the times of the spikes change, this input changes, and we will see that this makes life much harder. Okay. So what is our sorry? Yeah.
So if that's the quality of the neuron, right? It's not an input.
So x of t is we can see it as the input, but in this case, this input is generated by integrating incoming spikes. So every spike causes, you can model it as causes an exponentially decaying current, and this current is integrated by the membrane potential and produces this double exponential postsynaptic potential. Okay, so what do we want to teach our neuron? So let's say this is the input that we need, that we want, and we need this the neuron to learn not to spike in this time where it currently spikes with this synaptic rate, but spike at some other times, TD1 and TD2. And also we don't want, so it was a good question, what kind of accuracy do we need in the output? We don't want it to be exactly 10 to the minus 6 seconds. So we specify some tolerance window. So we want the neuron to spike one spike at this interval from TD to TD minus some epsilon, and one spike at this interval, and not to spike at any other time. Okay, so this is the task, and we want to develop some fairly simple learning rule that will enable to do this. So intuitively, what I would say is, listen, here you didn't spike, the membrane potential was too low, so you need to potentiate the synapses, do long-term potentiation, LTP, and every synapse you need to, you change every synapse according to how much it contributed to the membrane potential here. And here we had a spike that we shouldn't have, so the membrane potential was too high. Let's do LTD. Let's depress the synapses and push the membrane potential down. Okay. So this is what we will want. Want to do. So if we have no spike at the desired time, like here, so we change the synapses proportionally to the contribution to the membrane potential of each input afferent, this xi at the desired time. And if there was a wrong spike at the wrong time, then we depress the synapses, we do LTD, and so x's are all positive, so minus means you decrease it, we do LTD, and change each synapse proportionally to the contribution of its afferent to the membrane potential at the time of the wrong spike. Okay? But we don't have just one error, we have many errors. So for example, in this example, we have 4 errors. We have no spike here, 2 extra spikes here, and no spike here. And the question is, from which should we learn? Okay, which error should we learn to do this correction in order to converge to a solution? So the most simple choice would be no guess? So, I mean, you could say, why not just learn from all of them? Okay, let's take accumulate all the errors from this trial, then change the synapses according to the rule that we've seen from all of them. So this fails miserably, and I want to explain why. So let's take a very, very simple example. So here we have a neuron with a single input, one input neuron, that fires one spike at t equals 0. So what happens? There's beginning some postsynaptic potential, then there's a spike, reset, etc. That's it. And the goal of the readout neuron is to fire here, between this line, this is the desired time, and this is the tolerance window. So we need to fire between here and here. So what I'll do now, I'll do this small simulation and run the learning. And every time there are errors, for example, here and here, we do learning from both of them. We just add all the corrections and change the weights and run it again. Okay, and so these are green because the green color marks that we learn from this error. So everything will be green. So let's see what happens. Okay, so here you see the iteration every time. So you see here we have an extra spike, and here we have a missing spike, and the total contribution from learning from both of them, the effect is that the synapse increases, strengthens. So what happens? These spikes happen sooner, and the membrane potential here increases until we have another error there, and then the algorithm just basically is stuck. Okay? So this is because the net effect of learning from these two errors is to increase the synapse, whereas what we really need to do is decrease the synapse in order to get this spike closer to here. Okay, so you can say, okay, so this is because you add many errors together and this can fail. So let's see what happens if instead of choosing all the errors, I choose one of them randomly. Every time I'll just choose one error and maybe this will work. Okay, so this is what happens. So now all the errors are marked with gray, and the green marks the error I learned from. And you see that this doesn't do any better. Okay? Again, so every time I do here, I increase, this goes by, and then it goes back and forth, and more spikes are generated, less spikes are generated. It does really crazy things. Okay? And the reason these two schemes fail is exactly because of this nonlinearity of the reset. Okay, because we have a reset here, it means that this, if we don't fire here, it's not actually a mistake. Right? We don't fire here because we already had a reset. Okay, if there was no reset, then the potential will be too high here. Okay, and we will want to decrease the synapse. Okay, so the nonlinearity of the voltage reaches is that after a spike prevents the simple learning rules from converging to a solution. Exactly because if we have an error and we don't know how many resets we had in the past and when were they, we don't know if let's say we needed to spike and didn't spike. If we increased the synapses, we don't know if we didn't spike because the memory potential was actually too low, or because we just spiked 50 milliseconds before and we still under the effect of the reset. Okay. So what is our solution is to try to negate this problem in a simple way, is to do exactly the simple perceptron-like learning that we discussed, but only from the first error. Okay? So this is the finite precision algorithm. This is an algorithm that works. I will show you. And actually, we proved that it converges. Yes?
So what happens if you just don't take the reset so seriously? Because maybe it's not that big of a problem.
What do you mean?
Actually, lambda neurons, for example, don't reset so strongly as integrated time neurons. So they actually go very close to where the threshold was, and they pretty fast forget that they actually spiked. So what would happen if you change the kernel of the reset to be not so strong? Would it be able to convert?
So, you can ask me, even in the linear integrated fine neuron, you say, let's say the spikes are really far apart. Okay, the firing rate is very, very low. So basically, if I have an error now, and before that there was a long period where I didn't have any spikes, not undesired or desired, then basically the history doesn't matter. And you're right. Okay, so, but on the other hand, every time you have, if you do have spikes, then the effect of a wrong reset or an extra reset or a missing reset can accumulate for a long time. It doesn't necessarily decay, because you miss a reset, and then where you should have had the spike you don't have, and it's an effect that can go on beyond the time constant of the kernel of the reset or of the memory potential. Okay, so in principle, it's a problem, and whatever kernel you use. In practice, there may be situation where it's not very important. Situation when it is important. Okay. So the advantage of learning from the first error is that every time I only have the first error, I know where all the other resets happened, because I know. Let's say here I don't have a spike. So this is the first error. So I know, because there were no desired spikes before this time, that until this time there were no resets. And if the error would be here, let's say I don't have a missing spike, this would be the first error, then I know, because this is the first error, I know that here there were no spikes, here there was a reset in this time window, here no, and here there were no spikes, and here, okay, here I miss. And then I know that the correction that I make is in the right direction. And in fact, it's not possible to prove that this algorithm converges all the time, but in very general circumstances, we proved mathematically it converged. But if you don't believe the mathematical proof, so here is the example, in a simple example that this converge. Okay, so but this is a pretty boring example. So the synapse is just depressed all the time because you only learn from this mistake until it reaches the tolerance window. And here's a more elaborate example. So now we have a neuron with several inputs and several desired time, and I'm showing you the process of learning. So you see that it learns to spike here, then it learns to spike here, then it learns to spike here, then it learns not to spike here, and it does it in kind of a sequential manner. But it's important to know that it's not. There's also an example here, but it's not like that you always learning order. Sometimes something that you learn here may mess up what you learned before. So every time you go back, fix it, and go back and forth until you converge. Okay? Good. Questions?
So the mathematical proof you said doesn't depend at all on the specific parameters used?
No, it doesn't. It says that if there is a solution to this problem, so if you have some problem that satisfies some condition, extra conditions, so it has to have not any solution to the problem. So a solution I call a weight vector that produces the spikes inside the tolerances. Okay. So if you have a solution that satisfies, in addition of being a solution, some other conditions, then this algorithm will converge in finite time.
Right,
That's the theorem.
Define like desired spike trains that are not possible to learn to produce. If you're saying that only for a specific subset of possible spike trains.
No, so the convergence proof is that it doesn't say that if the condition do not stand, then the algorithm will not converge. In fact, we have examples of where the convergence proof doesn't work, or it's not applicable, but the algorithm converge anyway. So it's kind of a lower bound on what can you do. Yeah.
So the algorithm is to first correcting the first mistake, then the second, then the
No, every time it's the first mistake.
and then go on.
But every time it's every time the first mistake. But the first mistake at every time happens at a different time.
Does it happen that you can like interrupt?
Yes. For example, here you see when you learn this, then this goes outside of tolerance. It's hard to see, but then you go back to this and then go back. But even the importance of the convergence proof said that even though you go back and forth, it will converge eventually. Yeah.
Biologically, what's the time scale of this happening? So you have T is a certain time, but is that a second or within minutes it learns to adapt?
So there are two kinds of time. This is time of the input and output. So this is every time I present the input, the stimulus, and there are some input spike and then output spike. So this is this time. So this could be, I don't know, a second or 2 seconds or something. But every time, but the learning is an iterative process that we present a pattern, change the synapse, present the pattern again, change the synapses. And this and this is a different time scale. Okay, how many pattern presentations do we need? And this depends on how many do we need. Depends on how difficult the task. Can be a lot, but can be. It really depends on the details of the task. Okay, an important question is how many output spike times can one neuron learn? So we have this algorithm that we know will converge, but is this task even reasonable? Can this task be be done by neuron in a substantial. Can a neuron only learn 1 or 2 spikes if he wants to fire precisely like this, or can he learn 1 spike per synapse or something like that?
Doesn't it depend heavily on the eye size?
Yeah, so it depends a lot. This depends a lot on the task, whether the task is difficult or easy, or what are the statistics. So as a benchmark, we take a very simple task where the input and output transformation is random. So we take some. We have the input afferents, and we randomly choose their spikes from Poisson distribution or something like that, but only once, right? And so we do it once, and then these times are set. And for this input pattern, we randomly choose some desired times, and we ask ourselves how long, what is the number of output spikes that we can learn, that the neuron can implement. So this is the capacity of a leaky integrated and fire neuron. Okay, and what is interesting about this question is that the leaky integrated, this system have a lot of time scales, right? So we have the input rate of the neuron, the number of neurons, 1 over the ISI between the desired output spikes, the membrane time constant of the neuron, and the question is how does all these time scales interact with one another and relate to one another and affect the performances? Okay, is it easier to learn when the output spikes are far apart, or is it easier to learn when they are close together, etc.? So here is the summary of all results. So there are 3 main points. One is that the number of spikes that you can learn is proportional to the number of synapses. This is a good result. Yeah, everything, the inputs and outputs are uncorrelated. Okay, so one result is that all the spikes are random and independent Poisson processes. The spikes are drawn from independent Poisson processes. Okay, so first of all, the capacity is extensive. It means that it scales as you increase the number of neurons, you get more memory, and that it mainly depends on the output, the sparseness of the output. So how many output spikes do we have in one integration time constant of the neuron, and also depends strongly on the tolerance. So when the tolerance is 0, this is this line, okay? And when we increase the tolerance to the parameter is RR time epsilon to 10 minus 2, we get this line. But when we have R out epsilon order 1, okay, so the tolerance window is as large as the ISI between the desired times. So basically, we do not restrict the neuron to fire in a specific time. Then we get a much higher capacity because the neuron can choose actually where to spike. Sorry? Yeah, so for this we usually we don't, the fine precision learning will not be, probably be suboptimal, and you can use Temporal or something. And yeah.
This is simulation, right?
So this is a simulation and theory.
So shouldn't the curve for epsilon equals 0 be flat on 0? And how can you?
No, so we can. We didn't discuss it, but we have a different algorithm to find if there is. So if you want infinite precision, you can have a definite answer. Is there a solution or is there not? So then we have an algorithm that is guaranteed to converge. Yeah.
One thing that is very confusing is the number of spikes in the output is dependent on the total time. I mean, everything is in terms of rate, except that the synapse is a constant number, and the number of output spikes is a function of time. So how do you scale it? Doesn't it really make sense?
So I mean, you can think about it in 2 ways. I don't have the graph here to show you the results, but you can either say what is the duration, the maximal duration TC that I can learn, but this is equivalent of asking how many spikes, desired output spikes I can learn, because here in this task the output spikes are just randomly chosen with some mean rates
So wouldn't you want
are
to
out.
change n spikes to some multiplication or ratio between n spikes and TC?
Yeah, you can do that. You can, and we did. I don't have, but so then the graph just looked. You get the same. You get similar results, but the axes are different. But you can present this result instead of n spikes divided by n, but TC divided by n.
So this is for a given TC. That's what you want.
No, when you increase when n spike increases, it means that TC is longer. Okay, so I have a constant output firing rate, R out, and then I try to learn 500 seconds.
So it's for
And if R out is 1 hertz, then this is n spike equals 500. Okay, so it's completely equivalent. So the take-home message from this graph, so we have a lot of parameter, but if we want to summarize it in a sentence, is that it takes between 3 and 5 synapses to learn 1 output spikes if the precision that you want is a few milliseconds. Okay, in some relevant parameter range. So if the output is between 5 to 10 hertz, an integration time of 10 milliseconds. So this is for biologically relevant parameters. Yeah.
But this is sort of an upper bound, right? Because it may not be that real biological neurons can do this kind of learning.
No, this is true. This is strictly upper bound. Yeah. This is the capacity for a Leaky integrated inferred neuron for the relevant precision and parameters. Okay. So in the time I have left, I would like to discuss two nice biological applications of the rule, of the learning rule that we thought of that would be possible. The first one is reconstruction of synaptic weights. So let's say we make an experiment in a few years and we can record the activity of a local neuron circuit. So we get all the spikes of a few thousand neurons in some region of the brain. The question is, can we, only from the activity of the spikes, reconstruct the connectivity, the synaptic weights, between the neurons without slicing the brain and passing it through an electron microscope and tracing all the neurons? So can we, just from the recorded spikes, reconstruct the synaptic weight? So we can formulate it in kind of a learning. So this is the same setup that we have, kind of a learning problem. We have the recorded spikes of, let's say we want to reconstruct all the input synapses of one neuron. So we have all the inputs, the spike that we recorded, and we have the output of the neuron because we recorded this neuron as well. So we can treat it as a learning problem. What synaptic weights will take these spikes and produce this output? Sorry?
You're showing uniqueness to your solution. I mean, in the previous work you're not committing
Well, if you have, well,
one solution, right?
well, it depends. If I say if there is if the neuron, the model, okay, this is the answer. If we're talking about a Leaky integrated inferred neuron, so let's say the brain has Leaky integrated inferred neurons, then if you have enough data, then there is only one solution. Okay, there will, because to have a specific okay. Another caveat is that you really need to have really small tolerance. So for epsilon equals to 0, for precisely, if you have exact times, then and you want to learn with exact time, then there is if you have enough data, there is a unique solution.
This means that in a way you learn, so you learn your n spikes from before, say,
Mm-hmm.
and then all the rest is like kind of you just feed it through the same way, and it will just generate the rest of the
It means that if you have enough data after learning, you will have a precise model. If you give it new input, then the output spikes of what you learned and the output spikes of the real system will be the same. Yeah, exactly. So this is what we will show, but we want to do it in a more, so because the brain doesn't have a leaky integrated fine neuron, so what we do is we take a conductance-based Hodgkin-Huxley neuron, okay? And so this is like the neuron that we recorded from in the brain, and we learn the input-output transformation with the fine precision algorithm with the leaky integrated fire model. So here there's an issue of a mismatch between the real neuron in the brain, in this case the Hodgkin-Huxley neuron, and the neuron that we learn with. So basically, in general, there might be no solution at all. So there is no set of weights that can exactly reconstruct the spikes of the Hodgkin-Huxley neuron with the leaky integrated fire neuron, because the integration mechanism is different and the spike generation mechanism is different. Okay, but what we show is that we can do reasonably well even with this mismatch. Okay, so what we see here, so we take a Hodgkin-Huxley neuron, give it some input spikes, record its output spikes, and then use the input spikes and the output spikes of the Hodgkin-Huxley neuron to teach a leaky integrated fire neuron this input-output transformation. And this is the result. So here we see the reconstruction. So we have here these are the synaptic conductances of the Hodgkin-Huxley neuron, of the teacher. Okay, so inhibition here and inhibitory synapses here and excitatory synapses here. And here are the conductances of the student neuron, the one that were taught the spike, the leaky integrated fire neuron, inhibition here and excitation here. And you see that there's a pretty good match between them. Of course, it's not perfect because, as we said, there's a mismatch between the models. And so when for very weak synapses, the correlation is less good. But for very strong synapses, then the reconstruction works really well. And here's an example of the output. Okay, so in red you see the output of the original neuron for some inputs, not seen in training. And black, you see what happens if you take the reconstructed weights, put them back in a Hodgkin-Huxley neuron, and activate it with the same spikes, and you see that the output is very, very similar. This is typical error 1 in. There's an error in the spikes for every 1 or 5, 6 spikes. That's the best. These are the best performances. Okay. This reconstruction quality. So you say, okay, but how much? There are two important questions. First is how much data do we need to record from the brain in order to get this high reconstruction. So we measured this. So you see that the result that I showed before, we had 3 seconds of data of input and output per synapse to get this good reconstruction. But you see that even for only 1 second per synapse, you get reasonable performance of R square of the order of 0.9. Below that, there is a big, the performance really degrades. And also you can say, here we assume that I can see all the inputs of the neuron. But in reality, it will probably never be able to record all the inputs from the neuron, and the neuron can receive some input from other areas that we cannot see. So what happens if we try to learn not with all the inputs of the model neuron of the Hodgkin-Huxley neuron, but only some of them? So also you can see here. So this is the result. So the x-axis is how the fraction of the number of neurons, input neurons that we use for learning, and you see that above 80%, we can get a good reconstruction. So the bottom line is that we need to record at least 1 second per synapse and 80% of all the inputs of the neuron, and then we can have very good reconstruction of the connectivity matrix. Questions? Okay. The second application I want to talk about is
One more question.
yeah.
What happens when you do have correlation? If you assume it's no longer
Correlations in the input or in the input? No, in the input. Okay. Well, the output is generated by whatever the neuron does. Okay, it's not. So there are correlation in the. But but this is a good question. If you have correlation in the inputs, then it can bias the reconstruction.
do you do probably what you did before, where you randomly generate the output. So there is no.
I randomly generate the input, but the output is generated by the neuron. The neuron has some synapses, random synapses.
But you learn them.
No,
Feed them through some random synapses.
No. The model neuron has his own synapses. They are fixed. They do not change. And the student neuron tries to reconstruct them. So the neuron, the output of the neuron, the output is whatever the neuron does with its synaptic weight. It's true that the inputs are not correlated. There is no structure in the inputs. So these are random Poisson spikes. So if you have correlation in the inputs, it might bias the reconstruction. Sorry? It's not a matter of implementing a difficult computational problem, because the neuron has its synaptic, the model neuron, the Hodgkin axis neuron, has synaptic conductances, and whatever input you give it, it will generate an output. It doesn't do any specific computation.
No, but it could be that the neuron is spiking because of, say, subgroups of the input that are firing to delta, and this could be much harder for the algorithm to
Yeah. Yes, yeah, exactly. Because if you have correlated firing in the input, then it would be harder to distinguish the different synapses of these inputs, for example, because they will all look like one synapse. Or like if every time, imagine a situation where there are a few efferents that always spike exactly together. So the neuron sees them actually as one synapse only. So it, in principle, cannot distinguish between them in this case.
Did you look at what the relation between the cross correlation between the input and the output and your final synaptic point?
Sorry, I didn't follow you.
The classical way of reconstructing the connectivity matrix out of physics is to taking just the cross correlation between every one of the inputs and the output,
Yeah.
and compute the cross correlation and say, I don't know, the area under the cross correlation or the peak of the cross correlation, something in that function would give you the synaptic point.
Yeah.
This has been shown to not really work so well. But have you looked at what's the relation between the cross correlation and the synaptic weight?
No, we haven't. I mean, the advantage here is that you actually the numbers that you get for synapses are supposedly physical synapses. The efficacy of it's not some functional connectivity or some average quantity.
But it could be that actually what you find out after running this whole complicated algorithm is just a cross correlation. Maybe that's exactly what you find out, and actually there's nothing in the algorithm that suggests that you'll find something else. It would be kind of interesting to look at.
I agree. We haven't compared it to cross correlation. Okay. So the last thing I want to talk about is another example, this time from the birdsong system. So what we wanted to know is we wanted to do two things. The first thing, we wanted to to see. So up until now, everything, all the inputs were synthetic, random Poisson spikes, no correlation, etc., etc. And want to see if the learning algorithm can learn with realistic spikes that have variability, noise, and structure. So what we did, we turned to the birdsong system and tried to use the algorithm to learn something from the activity of premotor activity of premotor cortex neurons. So birdsong, we are talking about zebra finches. They have some repeating motif that they sing all the time or many times. So here's an example of a motif of one song. And Ben Solvetzky from Harvard recorded from area RA, and the neurons in RA, not like HVC, they fire the activity during this song looks something like that. So they have stereotypical spikes at given time. So here this is time, and the y-axis is the repetition of this song. Every time the bird sings the song, we get one line of activity. So you see that the neuron fires in bursts at this neuron fires in bursts, several bursts at these times. Okay, but if you want to learn from these spikes, we need to have recording of many neurons. So that's what Benson did. He recorded from 27 neurons, not at the same time, sequentially. But if we just take, one repetition of the song from each neuron that Benson recorded from, and just paste it and just put it together. So this is what the activity in RA in this area looks like during the song. Okay, so now each line is a different neuron. Okay, and the spikes are the response of this neuron to a certain repetition of the song. So when you look at it, it's very hard to see any kind of structure or to correlate, the pauses of the song or the onset of the syllables with this. And actually, we try to quantify it and find any kind of correlation, and nothing came out, at least not with this small number of neurons. And the question is that we wanted to ask is what happens if we try to take these input patterns and trying to have a readout neuron that will need to spike at specific points in time during the song. So the desired output of this readout neuron would be these lines around the onsets of the syllables or the peaks of the first peak of each syllable of the song. Okay, and biologically it may be, it can be used. Sorry? So this can be maybe used for learning, as this neuron can keep some information about the time from the activity of motor neurons. Okay, and then it can compare it to the time coming from HVC and see if there is a mismatch, and it can be used to learning some kind of efference copy of what the motor system does, doing some production that it can later be compared to the audio signal coming from the audio system. So we use the fine precision learning, and this is the output of the readout neuron after learning. Okay, so you see that it can learn to spike at these times. Of course, it has some errors. It's also interesting to see that this spike seems a bit difficult. It kind of misses it, but even though it misses it, it knows it produces the right answer for the spike after that, even though we learn sequentially. So it kind of looks strange, but the few times that you do get this spike right are enough to learn the other spike as well. Okay.
Where's the noise coming from?
So these patterns, every time I produce this input pattern, I choose a different repetition of the song from. So the variability comes from the variability of all the individual neurons. Then we said we wanted to see quantitatively what can we say quantitatively about this activity of the RA neurons. Okay, So we want to estimate how precise time is represented in the activity of RA neurons. So to do that, what we do is the following. Let's say now we have a different task. Instead of asking the neuron to spike at different times, we choose one time, some random time inside the song for the neuron to spike. And of course, how the performance of the neuron will depend on this tolerance, how accurate we want the output spikes to be. So this, if we have a big tolerance, it will be a pretty easy task. And if you want to have very accurate firing rate, it will be harder. So what we can do is to train the neuron with different tolerances and measure the error. How well can the neuron perform this task for the population? So if you do that, let's say you take 100 neurons, then you get, and the x-axis now is this tolerance, epsilon. You get this kind of curve that looks like an error function with some typical scale. Okay, and we take this typical scale to represent the accuracy that the neuron can infer. Okay, this epsilon bar, and as expected from the theory of population coding, as you increase the number of neurons, this epsilon bar scales like 1 over square root of n. Okay, and that's why if you plot it against square root of n times epsilon, all the lines are drawn, correspond one on top of the others if you change the number of neurons. Okay, so we can look at this scale. You can look at this time scale, epsilon 0, as like the single neuron temporal imprecision. How imprecise are the spikes of the neurons in RA? But notice there's the functional dependence on tau, because this is after the output neuron already filtered that spikes with some time constant tau. And we can ask, how does this imprecision of the activity in RA changes with tau, with the temporal membrane, with the time constant of the neuron, and we see that it decreases as tau decreases. So for this task, it's better for the neuron only to look at spikes of the past few milliseconds, because any integration over time just averages everything out and doesn't contribute to the information. If we compare it, but why is this surprising? This decrease when tau decreases. If we compare it, let's say, to an optimal observer, let's say you look at some time on all the spikes at some time windows of time tau and ask, what is the time in the song, just from observing these spikes. So you can do maximal likelihood estimation, and you can calculate the same quantity, and this is the result. So this is epsilon 0 of the neuron, of the readout, leaky integrated readout neuron, and this is the estimation for the maximal likelihood. So for the maximal likelihood, the more data you have, you have a better estimation of time, so the imprecision decreases as you increase this window. But what is interesting is that in the limit of this window being very, very small, we get similar performances. So the leaky integrated neuron is, in some sense, with a short integration time, in some sense does the best job anyone can do with these spikes. Questions? Yeah, we haven't tried it, but anyway, we take, the thing is that we take a lot of data, and in fact, there is basically in many situations, there is no solution to all the spikes. There is always some error. So in a sense, so learning doesn't converge. You never get to zero error on the training. So this annealing, I don't know. I don't know what will it do, but we haven't tried it. It might be.
What will the algorithm do when you hit an error? I mean, it has to overcome the error on one spike in order to get.
No, the error. It's true. It never converges. The error goes down, then it fluctuates, and then we stop after when it reaches the maximum error. But this is a question that is true for. It's not unique for Leaky and fire. It's also with weight-based model. What does the perceptron do when there is no solution?
No, but I mean, because you always take the first error, so can't you get just stuck on one spike that never comes to the right time?
So what we do is we present many patterns of. It's not like one long pattern. It's every song is 800 milliseconds. So we present it. So it's true that there may be that in a particular song you will never reach the end. Okay, I'll summarize. So for the first time, we calculated the capacity of Leaky and fire neuron to generate precise spike time sequences. In theory and simulation, I didn't discuss theory. We've shown that the capacity is extensive, so it's proportional to the number of synapses, and we derive the dependence on the different timescales of the neuron. And the take-home message for typical parameters: 5 plus 6 synapses are required per desired output spikes. And we developed a simple biologically plausible learning algorithm for learning these spike sequences with some pre-assigned precision. And we claim that this can be used for reconstructing synaptic weights from activity. And if you do the calculation, then you see that if you ask how many neurons in RA are needed for a readout neuron to spike with 1 millisecond precision, then the answer is that with around 300 RA neurons, a neuron in the brain with a time constant of let's say 10 milliseconds can learn to spike with millisecond precision at given times of the song. This we skip. Questions? Thanks.
We have time for a couple of questions.
So I have one
Yeah.
or two. One is this number of synapses you need to learn one spike, one output spike. How it relates, what will I do with it if I want to understand learning in a way? And the number also changed in your presentation from 3 to 5.
Oh yeah. No, it was 3 to 5 and then 5. It depends on a few.
But not 1 and not 100.
True.
That's what you mean. So what is the essence here? What does it mean? How complicated a network should be to learn a complicated task, given what is the assumptions that you will need, right?
Yeah, I mean.
What does it mean for me? I want to learn to differentiate between red and green? Or something
Well,
complicated?
these are
What do I take from the model?
well. This is the capacity. The capacity here is the capacity for these type of tasks when the desired output of there is some desired sequence of spikes that you need, but for example, if you would just want to fire at 100 hertz or not fire at all, it's a different task. Okay, and we showed it where when the tolerance window is very large and the capacity increases. So first of all, so this is one of the things that we learn, right? That the capacity of a neuron is dependent on how temporally precise you want to be. But if you do have this kind of task, then this calculation tells you how much can you learn. I mean, let's say a monkey needs to tap his fingers really, really quickly in some order, and let's assume for a second that this requires some neuron to fire at specific times quite precisely, I don't know, 10 millisecond precision. Then you will have an estimate of how much can this monkey learn?
Yeah,
So-
so the songbirds, they learn this song.
Mhm.
So I would expect at the end of your seminar to hear how many synapses were necessary to generate a certain sequence. For example, because this is something you do, right?
What?
So for my intuition, I would like to understand what does it mean? What does it mean for the network complication? You know that this song, this bird can produce this song. How many synapses are required? How many synapses are required to generate?
That is a good question. I agree. Okay. We have 5 minutes, no? We have 5 minutes, no? Ah, the clock is wrong.